This is the Automotive Repair Podcast Network.
Welcome everyone to yet another episode of Diagnosing the Aftermarket A to Z. I'm Matt Fonzel, and you could set your heart by this watch. That and more after a word from our sponsors, Pico Technology and Autel. Are you chasing elusive automotive problems? Pico Technology empowers you to see what's really happening. Pinpoint faults in sensors, wiring, and components with unmatched accuracy. Picoscope oscilloscopes transform your diagnostic capabilities. Visit picoauto.com, that's Pico auto.com, and revolutionize your diagnostics today. Autel delivers award-winning automotive diagnostic tools trusted by technicians across North America. Backed by Autel North America experts in sales, training, and technical support. From drivability diagnostics and TPMS service to ADAS and advanced safety systems, Autel helps technicians follow OEM procedures and repair with confidence. Learn more at autel.com. There just isn't that many quotes in media about aliasing. I didn't really ever watch the show Alias, and those that you did, maybe you recognize that one, but what do you do? The reason I bring it up is I've got a couple of emails asking me about aliasing, specifically oscilloscope aliasing. And the questions for one are, do all oscilloscopes alias? And that's kind of I don't want to say a vague question. It sort of is, because I think the ultimate answer is yes. Do they alias all the time? That's also kind of an interesting question, because when you start drawing the line, and there are specifications, right? When the manufacturers have specifications about like a bandwidth, there has to be a certain level of accuracy. Anything outside of that, is that when you're going to start calling it aliasing? And really, if we define aliasing, we would say it's the inability or the failure to accurately reconstruct the waveform or signal that we're testing. Well, if we use that really strict, and maybe I'm taking a little bit of creative license with it, it kind of takes you to an interesting discussion of like audiophiles. And I don't know if any of you know a real audiophile. And I'm trying to think of a friend of mine in the profession that I could bring up who is a tried and true audiophile. Usually one of the dead giveaways is their stereo systems are large and expensive. The reason being is they want to hear as close to the either studio version or the live version as possible. And so I guess why I bring that up is you kind of have a debate from audiophiles and to just avid listeners that the only way to truly listen to all of a song without any missing bits and pieces is with a record, analog, and any analog means of listening to the song. Okay. Not digital. So not MP3 or MP4, any sort of audio file like that, like FILE file, not PHIL file, not CDs. So therefore, the debate is when it's digital, there's little bits and pieces missing. Whether somebody can truly hear that or not, I don't know. Maybe years and years ago, maybe. Nowadays, I don't know. With how good like DA converters are and stuff like that. The reason or the method to my madness, if you will, as to why I even go down that road is comparing an analog lab scope or an analog scope to a digital storage oscilloscope, like what most of us are using. If it's digital, technically there's samples, right? So there's technically missing pieces. Again, does it matter? Probably not. So maybe the smart aleck answer is yes, they all alias. They certainly all can alias. That usually happens with poorly designed oscilloscopes. And we're talking, I'm going to speak almost primarily of digital storage oscilloscopes. That's what most of us are using. If you have a handheld lab scope, it is a DSO. PC based DSO. Okay. that's not inherently bad. There's many, many, many terrific advantages of having that. And again, I'm not implying that the fact that it's digital causes us to miss little bits and pieces, okay? But the way they operate requires that they have a certain build for the signals being tested. You may buy an inexpensive scope that for certain things works perfectly well. There's no reason to spend more money until you get into signals where they can't keep up. And now they're no longer properly reconstructing or accurately reconstructing the signal or the trace. They're in fact aliasing. And sometimes when a scope aliases, it's like missing pieces, right? Like there's gaps, like obvious gaps, and that can throw you off. You can start chasing something. Like if a engine is cutting out and your scope in the crank sensor, and either through the lack of capability of the scope, poor scope technique, you can see gaps, and it will make perfect sense that the crank sensor or reluctor or some sort of failure is occurring, causing the cutting out, when in fact the scope is not reconstructing the waveform properly, leading you down, the wrong path. So why does that happen? What's going on? And, when I first started looking at the emails and thinking about this episode, it's kind of like, I think I need a diagram. I think I need, this should be like a video and a presentation and, PowerPoints and slides and all that. And I'm not exactly sure that would help. I gotta level with you, because the numbers we're talking about are so absurd to try to wrap our heads around. Maybe this is a good flow to this, and maybe I'm backing up a little bit, but I think this is at least an accurate enough description for no one to get led astray. And some people, if you're big into scope design, maybe you can shoot this up a little bit, blow it apart. But I think for the most part, this is good enough to get us where we need to go, to understand kind of what's going on. And fortunately or unfortunately, I'm going to have to ask that we kind of use our imaginations, that we're able to picture certain things in our head. One of my favorite ways of thinking about how a digital storage oscilloscope works is to picture in your head a pegboard. If you think about that pegboard, it's got, holes in it where you would place your hooks. But in this case, let's just say we stick like a pin in there, or a peg, or like a golf tee. Okay. And we got whatever color for channel 1, pick your make, of scope. It's black, it's blue, it's green. Okay. That's the color of the peg. What this pegboard is representing is not the scope screen. Not every scope displays. The pegboard doesn't represent the screen. It represents the memory. Because remember what I said? We're talking about a digital storage oscilloscope. So that means it's going to sample. It's going to measure the voltage, because that's what they do. It's going to measure the voltage, and then it's going to pick up one of those golf tees, and it's going to stick it in the appropriate hole for, the poles going up and down are amplitude or voltage amplitude. And then left and right is going to be its place in time. But like I said, that it doesn't represent the screen. It represents the memory. So it's storing it in memory. And depending on the scope, will determine, and some setup, don't get me wrong, like ranges, both amplitude and time is going to have a role in this. But just for the sake of this discussion, the holes going up and down represent the voltage levels, the amplitude, but it's also the number of those holes, or how close they are together, how tight together they are, is determined by something called vertical resolution, which I don't know how terribly important it is to cover in this episode. We'll just say that the higher the vertical resolution, and generally the offerings we have typically are 8-bit, 12-bit. I guess I'm starting to see a few 14s, but a lot of times it's actually 12-bit, or they have 14 bits with 12 bits and they're using 14 and then 16. Those are the common ones. And the higher that number, the more of those holes there are in a given range, we'll say just a given voltage range. It's how tight they are. So you could say that vertical resolution allows it to be even that much more accurate for the voltage amplitude, right? If you look at something with an 8-bit scope, and we'll just say it's a 5.2 volts, maybe the 8-bit scope, the closest it can get is, depending on the voltage range choice. Again, I know I have to talk this way because that's the way it works. And it can be frustrating, but that's how stuff works. We'll just say that the signal is 5.2 volts, but the 8-bit scope, the closest it can get is 5.1 volt. Or maybe it's even further away, but I think that's fine. The 12-bit scope, maybe the closest that can get is 5.15. Okay. And then the 16-bit scope, maybe that can get 5.19 or 5.21, something like that. That's the closest it can get. And maybe actually get to 5.2. Maybe both the 12-bit and the 16-bit can get to 5.2. And then it's just how accurate and how fine of trace it's going to be up and down. That takes us to time. And that's not to just jump past vertical resolution, but where we really find scopes falling apart, especially if they're like a 12-bit and a 16-bit, where we find them really falling apart isn't in the vertical portion. 8-bit, they don't so much fall apart as much as you kind of get a stair step look to the waveform, especially if you're like zooming in. But where they typically fall apart is on the time portion. So now, again, digital storage oscilloscope, it's going to measure the voltage and plot the point. It plots it in memory. And the memory is usually referred to as either sample point memory buffer, or just the buffer. Those are the terms often used for scope memory. This is where it gets kind of tricky, because the common scopes that we're using in the bays aimed at automotive, the Snap-ons, the Picos, their memory specifications are in the hundreds of thousands, 500,000, and then millions, multiple millions. We can't picture that in our heads. This is a pegboard that's, however many, almost 4,096 holes going from the bottom to the top in memory, and then left to right. It could be 512,000. It could be 32 million. It could be 128 million. Like, those are absurd numbers. Even the 512,000 is an absurd number to try to picture in our heads. Like, it's next to impossible. Let's just kind of shrink it way down just to try to get a concept past. Okay. What if we have a scope that samples at a relatively, easier to picture a number of, let's just say 100 times a second, right? Sample rate is the number of times it can sample the signal, right? And that used to be such a popular specification. It's important. And what you learn about scopes, it's about relationships, right? The specifications, I suppose, not unlike race cars. Like, horsepower is important, but so is torque. So is gearing. Like, there's more to the story. That's kind of how scopes are. There's more to the story. We got things playing together that determine actual performance for us doing what we need to do with the signals we're going to be looking at. But just for the sake of discussion, this thing samples at 100 times a second. And just maybe to make things easy, the memory buffer is 100 sample points. Electric and hybrid vehicles are here, and with them, a new era of diagnostics. Don't get left behind. Pico Technologies EV diagnostic kits are your all-in-one solution to safely and efficiently service any electric or hybrid vehicle. From comprehensive high voltage system analysis and insulation testing to guided step-by-step procedures, Pico puts the power of confident repairs right at your fingertips. Future-proof your shop, boost your efficiency, and become the go-to expert for the next generation of cars. Visit picoauto.com today. That's PICOauto.com. This episode of Diagnosing the Aftermarket A to Z is brought to you by Autel. Autel is a global developer and manufacturer of award-winning professional automotive diagnostic tools and service equipment, trusted by technicians, educators, and shop owners across North America. With diagnostics at their core, Autel's real-world solutions support repair workflows ranging from full system vehicle diagnostics to servicing the most advanced automotive technologies. What sets Autel North America apart is the team behind the tools. Dedicated experts across sales, training, and technical support, each bringing deep, hands-on experience supporting professional technicians. When questions arise, you're working with people who understand the vehicles, the procedures, and the real-world demands of modern repair. Whether diagnosing complex drivability concerns, servicing TPMS systems, validating repairs, or working with ADAS and advanced safety technologies, Autel tools are engineered to support accurate, efficient repairs in strict accordance with OEM procedures and standards. To learn more about Autel and their diagnostic solutions, visit autel.com, AUTEL.com. We have our 100 sample rate scope with 100 sample points. If we put a second on the screen, if we have 10 divisions and we select our time base per division, it's not going to be 1 second per division. That would be 10 seconds. We're going to select 100 milliseconds per division to give us that 1 second per screen. And remember, in this example, the screen that we see is a real good direct reflection of the memory. That's not always the case, but that's for discussion purposes. If we have a sample rate of 100, sample rate of 100 times a second, it's going to measure that signal 100 times. It's going to plot a peg in our pegboard for, 1 second 100 times. It's going to be able to do that, right? The pegboard from beginning to end is going to represent 1 second, and the sample rate is 100 times a second. It's perfect, right? It's going to sample that 100 times. And that's what's going to be on our screen, or, could be, depending on the scope, 100 dots left to right. And then the scope connects the dots. That makes perfect sense, right? That would be good. But now what if we start changing the time base? What if we speed up the scope, like put less time on the screen? Okay. Instead of 1 second on the screen, what if we put 1/10 of a second on the screen, right? That's going to be much faster, or at least we're going to be zoomed in more, if you will. Maybe zoomed's a terrible word to use, but we're going to open that up, right? Well, we still only sample 100 times a second. Our screen now represents 1/10 of a second. So that would mean our scope is only able to sample 10 times in that memory buffer, right? It's not fast enough. It's not fast enough to fill up that memory. See how that works? See how if a scope doesn't have quite enough speed, it starts to fail to reconstruct the waveform properly, because at that time base, it just can't sample fast enough. It can't pick up enough samples. Let's go to the other end. What if I put more time on the screen? What if we put 10 seconds on the screen? Now remember, the screen, in this case, represents the memory. So we have 10 seconds on our screen, but it's going to be represented by 100 holes, if you will, 100 dots. Well, the ADC, what's going to do the collecting, still wants to sample at 100 times a second, and I have 10 seconds on the screen, but I have nowhere to put those measurements. So what does the scope have to do? What does it have to do? The sample rate doesn't actually decrease. It starts rejecting measurements because it can't measure or it doesn't have anywhere to place those measurements, it's probably going to skip, right? It's effectively reducing the sample rate because it doesn't have anywhere to put it. There's some scopes, if you watch, they'll have like a properties menu or dialogue or tab where you can watch this live. You can see what's happening. You can see how many samples am I requesting? How many samples am I actually getting? What is my effective sample rate? And you can watch this dynamic happen. Now think about what we're talking about here is when I put a lot of time on the screen, like in this case, we're talking about 10 seconds, we might fail to reconstruct that waveform because we just don't have enough places to put the measurements. That's the effect of having a low memory. You know, back in the day, we would use scopes like Flukes and Tektronix and all that. Their memory buffers were paltry for what we use it for. Their sample rates, extremely high. I mean, honestly, even now, by today's standards, most of what we're using weren't as fast as some of those. Some of those old Flukes, like the 90 series, I think the Fluke 97 and the 105, and I don't want to speak to the 98. I can't speak directly to the 98. But the 97s, I think, and the 99s, I'm pretty sure those were gigahertz level. And I know a lot of the Tektronix scopes started out at 250 million times for their sample rate, 250 million times a second and 500 million times a second. And I'm pretty sure 1 gig a sample per second. It would be like the THS 730, if I remember right. Probably should look it up. The memory buffers are small, but they were looking at super fast signals. They didn't care. They weren't trying to collect 1 second of data on a screen. That's just not the way they were used. And in our world, it turned out for like, at least the Tektronix versus Fluke, the Tektronix had like 2,500 point memory buffers. They did a little bit better than the Flukes. I mean, you got to call a spade, right? What really brought this to our attentions was the Pico scopes. It'd be like the 212 series. The cases were white. You had to have them plugged in either to the car battery or to the wall. You had to be careful. If I recall, at least for the 212-3, you had a 30,000 point memory buffer, which at the time blew everybody out of the water. It wasn't even close. So what you could find is with the Picos, even though their sample rates weren't just blazing fast, they weren't slow, don't get me wrong, but they weren't like blazing fast. They had so much memory compared to the competition at the time that they could record the very accurate waveforms with a lot of time on the screen. And then we could zoom in for detail. That's where they really shined and arguably still do. It's just now they've got the speed to do stuff, you know, fast. And I don't mean this to be a Pico commercial. I'm just trying to explain how the things work. But we find that because of that, a lot of the automotive scopes are offering that to us and giving us bigger buffers. The Snap-ons did that. And I'm hoping that that explanation kind of makes sense where you have to pay attention and know your scope. Know the specs a little bit. Know where its strong points are. If you've got more of an industrial scope that doesn't have a lot of memory but tons of sample rate, it's probably meant to look at stuff very, very fast, not a lot of time on the screen. You get a lot of time on the screen, things fall apart. If you have other scopes, maybe older ones that had a fair bit of memory but they just don't have a lot of sample rate, they could look at, you know, relatively slow signals, if you will. And I use that word hopefully accurately, relatively. You could pack a decent amount of time on the screen and zoom in for detail. The newer ones, of course, there's just a lot more leeway, a lot more sample rate and monstrous memories. So you can pack on a lot of time on relatively, not even relatively, like fast signals and zoom in for detail. Now, I don't mean this to call anyone out. I don't mean person, but scopes. Not all scopes display their buffers the same way. All right. The displays themselves don't work the same way. With a Pico, if you set it up a certain way, the screen you're looking at will be representative of the memory buffer. Don't get me wrong. There's more holes, if you will, in that pegboard in the memory than there is pixels on the screen. Okay. So it's not accurate like that, but it at least represents it. And again, you have to set the scope up a certain way to make that happen. The other most popular, as far as I know, and maybe the most popular scope out there is Snap-on, whether people know they have one or not. That the way the screen works, the buffer and screen relationship works is much, much different than everybody else. As far as I know, unless something has changed, the Snap-on scope, starting from like the original Modus and Vantage Pro all the way up to the Zeus Plus, and I could be wrong about the Zeus Plus, but I think I'm right. The memory buffers are 512,000. But the screen you're looking at, it's important to try to watch. This depends on which one you're using, but usually there's something called like a buffer bar. So on the old Moduses and the Vantage Pros, it was at the top of the screen, just above the scope screen. You could watch that thing fill up, and there might be a little, not like an arrow, but like a little bar that would fly across, depending on how much time you have on the screen. That left to right, that bar was a buffer bar that was representative of the whole buffer. The screen is like a little window into this big buffer. So you're just watching the buffer fly by through the screen. You could say it works backwards, or at least maybe 180 from, say, a Pico or an Autel, right? Where we can zoom in. Snap-ons don't zoom in, they zoom out. So what happens is a Pico, you might set up for a good amount of time, whatever that may mean, okay? You're trying to capture, we'll just say an intermittent. So you put, a couple seconds on the screen of a relatively fast signal, and you go drive it and you see or feel a bump, and you freeze the scope, and then you zoom in for detail. Snap-on doesn't work that way. You can't use it that way. And that's what happens particularly with the Snap-ons is the user doesn't understand the screen to buffer dynamic. So what happens is they try to put a fair bit of time on the screen. They want to see the dropout on the screen. And that's where things fall apart. Remember what I was saying about putting more and more time on the screen? You start running out of speed. The sample rate is no longer enough to properly fill that buffer. Okay? So we get gaps or just behaviors. Snap-ons, what I've seen is you get gaps. They look like dropouts. They're gaps. The scope just couldn't reconstruct it right. It might have a little bit to do with digital signal processing, but I think Snap-on's digital signal processing is actually quite good. It just isn't enough to make up for that. And arguably, it's a misuse of the tool. It's not to trash on anyone because nobody really taught it. Unless you were really paying attention back in the day on IETN and maybe Diagnostic Network, maybe you got into a really good class, back when Harvey Chan would do it. I think John Thornton and Scott Manna, their classes, they talk about that. And more, I'm positive Tim Iazzi's and Ira Waldman's covers it. It's so important, Scott Schotten, that the way you want to set up the Snap-on is the detail you want to see is what you want on your screen. Okay. So if you're looking for just an example, you're looking for a pintle bump on an injector, the voltage waveform. You want to see the pintle bump for whatever reason, just as an example. It's a relatively quick event. You have to get that on your screen and then go drive the car and wait for that misfire or whatever, the hiccup that you're looking for. And watching the buffer across the screen, that the little buffer bar, kind of that position indicator, how fast that flies across the screen is kind of going to help determine your chances of being able to freeze the scope fast enough to be able to see it. But what you would do is assuming this, we'll just say, for example, that buffer bar is moving across at a speed that still gives you a second or two to be able to pause the scope, freeze the scope. You can do that. Okay, you feel it. You don't necessarily see it on the screen because honestly, what is going across your screen is probably going to be unintelligible. You won't be able to process it that fast. But you feel the bump, hit the freeze button, and then you zoom out. You can zoom all the way out, and now the screen is representative of the entire buffer. And you can find a point of interest and zoom back in. But you can't zoom in any further than what you had on your screen. Okay. That's how you're going to use that scope. And hopefully that explains why and how scopes alias, especially ones that have, like dedicated buffers and the dynamic between sample rate and memory. I know it's a tough subject. I just don't know how you really illustrate it out on a screen. I suppose we could do the 100 dots on the screen, but it's still, I think you can picture it in your head. I think the pegboard works. And just that idea of the dynamic between the sample rate and the buffer. It doesn't have, you don't need intimate knowledge of how the scope works to prevent aliasing or recognizing when it happens, setting yourself up to succeed. Use the scope properly and where it's maybe potentially going to run out of steam. And there's, depending on what scopes you have, determine that. And you could have a really good one. Don't get me wrong. Like, I'm not calling out junk out here. You could have went and got yourself a nice scope, but it works a certain way. And you can help determine how that works looking at the specs. That's how I will leave you. Hopefully I didn't overcomplicate that, but it's a really good question. It's a really tough question. If you still need more or want to see that in action, of course, play with that in your shop, but also a hands-on class where they can demonstrate that for you and see that in action. It's tough to beat. So that's how I will leave you. I really, really appreciate you listening. I really appreciate the question and the questions that have been sent, the messages. Yeah, I can't thank you guys enough. The email is mattfonslowpodcast@gmail.com. If you have other questions, please don't hesitate to ask, automotive related or not, because really ultimately we're all humans. We work on cars, so therefore everything qualifies. Yeah, ideas for topics, guests. If you would really like to be a guest on the podcast, please fire me a message. You can also track me down on social media. I've been hiding from the hackers. Not sure what happened there. It's a while ago, but so far, no issues since. Thank you to our sponsors, Pico Technology and Autel. And thank you to the Automotive Repair Podcast Network for really making this all possible. And until next time, take care.
You've been listening to Diagnosing the Aftermarket A to Z with Matt Fonslow on the Automotive Repair Podcast Network. Download our exclusive podcast app at automotiverepairpodcastnetwork.com because the best conversations in the industry start here. Want Matt to cover a specific topic? Check the show notes for his email. Your input matters.